Thank you to Simon for inviting me to speak to you all at this Meshwork event. My name is Nathan Gambling. I host a podcast called BetaTalk, as Simon said. I've been involved in educating plumbers and heating engineers. I grew up in a heating engineer sort of environment. My grandfather was the one responsible for bringing oil technology to this country back in the 60s, 70s from Sweden. And he was one of the sort of scientists and research and development engineers that was looking into heating. He was a combustion expert. So I want to give you a little bit of a potted history of domestic heating. So I've found that having a bit of an understanding of how we start to heat our homes does help with what we need to do now. So hopefully you can see on the screen what I call point of use heating. So before we had central heating in domestic properties, we had point of use heating. So some of you remember the 3-bar electric fires that your aunts and uncles may have had. There's a range in there, there's the coal fire, and there's a gas fire. So we tended to heat the spaces that we were actually occupying, so point of use. Domestic central heating sort of came around in the 60s, really. Now, I want to sort of hit home a very important principle about heating. Now, obviously here we can see the sun. That's what gives our planet its energy. We get light and we get heat from it. The light is obviously turned into chemical energy via photosynthesis. That's all to do with the first law of thermodynamics. That's where we get our energy from. We eat the plants that have turned it into chemical energy, or the animals that are eating the plants. Now, the important thing to remember is we all are quite familiar with the term, the speed of heat. We know it's a constant. So the speed of light. We know that light has a constant speed, but very importantly, heat doesn't. Heat is constantly changes its speed. And this is something that the engineers, the forefathers of heating, really understood quite well, that the speed of heat is constantly changing. Now, some of you are going to be very familiar with this. This is kind of explaining the second law of thermodynamics. Here I've got a seesaw with a ball. Now, instinctively, we know that ball is going to move to a lower position. And that's the same with heat. Heat always moves from a high temperature to a lower temperature. And it will also move quicker, just like that ball, if there's a greater difference. So the ball is going to move quicker if there's a greater difference in height. Heat will move if there's a greater difference in temperature. And it's a very important concept that seems to have been lost. I've got a little picture here of a house. So here we can see at the top, we've got 21 degrees inside, we've got 10 degrees outside. So the speed of heat leaving that home, there's a difference of 11 degrees. Now, it doesn't matter whether you insulate a home, it doesn't matter how much insulation you put around a home, heat will still move. That's the law. You can't stop it, you can just slow it down. So if we look at the next one, it's 21 degrees inside, it's 6 degrees outside. And that's moving exactly the same speed as if we had 19 inside and 4 degrees outside, because they've both got a difference of 15 degrees. So the speed of heat leaving the home in them two cases is the same. And obviously, as we get colder outside, the speed of heat increases. Now, the engineers back in the days in the 60s and 70s realised that the best way to heat a building is to match the heat going into that building with the heat leaving the building. So it was our radiators generally that were emitting the heat into the building. And so you can control how much heat a radiator emits into the building by controlling the flow temperature going to the rad. And so they use controls in the commercial industry called weather compensation. So they had sensors on the outside of walls. They sometimes even put sensors into the walls that was measuring the temperature outside. And that meant they could adjust the flow temperature going to the emitters, usually radiators, sometimes fan coils in a commercial setting. So these are old weather compensation controls that someone like my dad would have fitted into commercial industry. Back in the domestic industry, we couldn't kind of do that yet. It was the boiler, and I'll explain it in a minute. The boiler needed a high temperature. The homes didn't always need a high temperature. As we've seen in the previous slide, the temperature that your home needs is constantly changing due to the temperature outside. The speed of heat is constantly changing. Now, many people think the TRV, which was invented in at Danfoss out in Denmark, and my granddad would fly out there quite a lot in the 70s. The TRV was actually introduced into the domestic market because homes were overheating. People would open their windows in their bedrooms, for instance. The wall stat was also introduced into domestic heating because our homes were overheating. You needed something to turn that boiler off. The reason they were overheated is because the radiators had a constant temperature, a very high one, usually around 80 degrees. So a lot of the time through winter, our homes would overheat unless it was the really, really cold days. Now, why did that boiler need the high temps and not the radiators? Well, the boiler needed a high temp because when you boil a fossil fuel, it's a hydrocarbon, which means you're going to get water vapor as part of the combustion process. If your return water back to that boiler was too low, the water inside the water jacket or the heat exchanger was too low, the water vapor would condense and it would basically rot the water jacket. It would destroy the boiler. So it was the boiler that needed these high temperatures. It wasn't necessarily the home. And as we've seen, the home is the speed of heat leaving the home is constantly changing. So these are why these things were introduced into the domestic industry. Now, back in 1973, I was only 2 years old, so I don't really remember it that well, but we had the fuel crisis. So the R&D engineers and scientists around Europe set about trying to come up with a boiler that could deal with this condensate problem so that they didn't rot. And in 1981, the condensing boiler first came to market in the Netherlands. My granddad was half Dutch. He was sort of part of lots of the R&D engineers in Europe were sort of working on this. So the mid 80s, late 80s, you could get condensing boilers in this country, and some of the really good engineers were sort of starting to weather comp them because it meant now that the radiators didn't have to have this high temperature all the time. You could have different temperatures going to the radiators depending on the speed of what your home, the speed of heat your home needed. As Joe will probably talk about, in 2005, we mandated the fact that we had to put condensing boilers in, but we're still in this weird position where we're controlling condensing boilers with a thermostat, an on-off thermostat. We're not compensating them. We're not getting different flow temperatures going to the radiators. 2016, we were the world's largest gas boiler market in the world up until 2016. And I think that's one of the main problems. We became so big, our industry, the control industry became very big, which is the TRVs, the thermostats, and the boiler industry became very, very big. I think it became just about selling that box on the wall. And unfortunately, all that sort of engineering knowledge that the forefathers of heating realised sort of kind of got lost. What also got lost was, the boiler industry turned it into kind of a white goods industry. Heating isn't about the heat source. It's not about the boiler or the heat pump. Heating is a system. And the way I tend to explain that is Usain Bolt is the fastest person on the planet, has a very, very super duper efficient heart. If you transplanted that heart into my overweight body, my defunct system, I wouldn't be able to run any faster. So we had a boiler industry sort of talking about their super duper efficient boilers, getting plonked on the wall, but it was the system that dictates whether you've got efficient systems or not particularly the boiler. Joe would probably speak more about that. So here we are in 2023, we've got 6,000 boilers going in every working day. Most of them, apart from sort of engineers, I and Joe know, most of them are going to be controlled with an on-off stat, which means the same temperature of water is always going to your radiators, so you're never matching that speed leaving your home. We had something called smart stats come around a few years back. Smart just means it's connected to the internet. It's an IoT device, Internet of Things. Some smart stats can compensate the boiler, so it can change the flow temps going to the radiator, but a lot of them don't. British Gas, largest gas boiler installer in the country, they've got their Hive thermostat, they own that. That at the moment is just an on-off stat. I have been badgering them about that, and they are apparently going to change the software this year and make it a compensation control. So that's kind of the state of play. We realised back in the day that to have an efficient system, you match the speed of heat going into your room with the speed of heat leaving that building. Otherwise, you're just switching things on and off, and you tend to keep going up and down with the temperatures inside, and you get more wear and tear on the boiler. So that's where we're at. Over to you, Joe.
Thanks, Dave. That was great. I learned loads. Fantastic. Okay, well, I'm going to speak to some of the points that Nathan raised there around perhaps the shortfall in performance for condensing boilers for a lot of the reasons that Nathan outlined. And I'm just going to wrap that into EPCs, because I think that's quite a familiar place for most of us to perhaps understand our homes and our energy systems. I mean, I know it's a very flawed process, but actually there are some interesting aspects to EPCs, which is that they recognise efficiency where building regs do not. So I think I'm going to go through that. So I'll share my screen as well, but also talk about the inefficiency of gas boilers. Right, I think I'm showing the right one. Yes. Okay, bit of an ominous image. Okay, so yeah, just an intro. If you're not familiar with us, we provide impartial and expert action plans to households to reduce their bills and decarbonise our heating systems. And at the core of our business is our impartiality and technical expertise. And their importance can't really be underestimated, because good buying decisions maximise your budget and expedite the energy transition. And without them, we're forced to engage with suppliers who are naturally biased or attempt our own research through usually supplier websites. And this nearly always results in a poor buying decision that we have to live with. So the foundation of our business actually can be found in the incredulity felt by Caroline and I on the discovery that households were routinely shortchanged on their boiler installations and running costs. Pretty early on we learnt that, and from people like Nathan and a real grassroots movement that was there before we showed up, we learnt that the gas industry was safe, but it was not concerned about the efficiency or longevity of its products. In fact, success is measured purely in selling more boilers, and this has led actually to a really inflated boiler market, and often bemusement from other European countries at our advice to change a 10-year-old boiler because it's approaching the end of its life, when it is in fact about halfway through its 22-year lifespan. But sadly, performance indicators such as poor operation or high gas bills have been concealed by cheap gas and a wide margin of error, which means gas boilers still work even when they're set up pretty badly. And as we have no indication of knowing how inefficiently our boilers are running, it's not like they have a digital display, so we've been unable to hold the industry to account. But actually, we've known as early as 2009 that about 83% of boilers in an energy savings trust study, 83% of A-rated boilers were in fact C to E rated in practice, yet nothing actually has been done, despite multiple uplifts in building regs, Boiler Plus, which I'll come on to remove low-tech models from the market, so really basic stuff that's still out there, or force higher installations to deliver an A-rated performance. So we offer a roadmap approach, and that's why actually step one on our roadmap is to make the existing boiler more efficient and keep that boiler until you're ready to fit a heat pump. 90% of homes already have an A-rated boiler, they've been mandatory for 17 years, and 99.9% of them can be made more efficient one way or another, for which you will also gain some EPC points. Not that we're really focused on that at the moment, but it's an interesting intersection, whereas another A-rated boiler will not. So with your new boiler budget, we really want to see that repurposed towards more impactful measures such as lowering flow temperatures through bigger radiators and preparing for a low carbon heating system, but also insulation, some low cost insulation out there that will have a much bigger impact than replacing an A-rated boiler with another A-rated boiler. At the end of the roadmap for most of us will be a heat pump, although it might be a communal system. There's lots of interesting models coming. I think it's worth me saying at this point, very few houses will run on hydrogen. We know the hydrogen lobby is in full swing, PR swing on this, but actually it's a long way away. We should be focusing on heat pumps and technologies that are ready to go. So for many of us, it's quite interesting just to track alongside the roadmap is the sort of EPC score, and they're made up of points range. So EPCE 39 to 54 points. So there's a big difference, about 15 points between the bottom and the top end of an EPC. And what we're all aiming for really is to get to EPCC. So you might be moving from the bottom of band E up to an EPCC that's 30 points. And just out of interest, I tried to look at the EPC projections of energy use for 150 square metre homes and look at the energy reduction between a midpoint in the E to the C, and it's 57% or £978 per annum. They're obviously fairly large houses. Yeah, so as much as possible, we are moving along an EPC route and we're moving along a decarbonisation route, and those two things do get reflected in EPCs. So on EPCs, it's just worth clarifying, and I've just put that letter wrong, so I apologise, what you're being scored on in EPC. So it's an energy efficiency rating, not to be confused with an energy impact rating, which scores carbon reduction and no longer features on the EPC. So the EER, not EEF as I put there, is a calculation based on 3 metrics: how well the property retains heat through insulation, efficiency and responsiveness of the heating and energy systems, and cost to run. This is based on fuel prices and affordability. The cost to run is a curveball. It means condensing boilers are on a par with heat pumps, as both are classified as very good, i.e. fitting a heat pump in place of an A-rated boiler at the moment will not improve your EPC score. So this is the interesting bit, the intersection between where building regs sit and where EPCs do recognise better measures. And it's important to understand that intersection, because there are untapped efficiency. It illustrates how there's untapped efficiency in our heating systems and also EPC points available. So at the moment, it's under building regs, you have to fit an A-rated boiler. We've known that. And in 2018, there was a boiler plus uplift. So this was a building regulations uplift. It focused just on heating control. So with the combi boiler only, so it didn't extend to system and heat only boilers, you could fit an advanced, or you must fit an advanced energy saving measure, and that can be a load or weather compensation control. So as Nathan was talking about, look at the outside temperature, look at your thermostat temperature, work out the difference, work out the flow temperature, and they were always continually working to reduce that flow temperature down in order for the boiler to condense. Or you could fit an automation and optimization control, which also, as Nate said, just a glorified on-off control really with a bit of internet connection, or you could fit a flue gas recovery unit, actually a much less effective measure that was sort of thrown in there as well. A wider building regs uplift came in 2022, whereby combi boilers must not be significantly oversized, very general requirements, not very impactful. And for full heating systems, radiators must be sized to run at 55-degree flow temperatures. I say must, actually, it probably says should. So again, it's not very loose. They're all very loose. And what they don't mandate is the most efficient measures of load and weather compensation controls. However, EPCs do correctly assign points to the highest efficiency measures, i.e. load and weather compensation controls. But as Boiler Plus was not restricted to these controls, they're not widely fitted, and certainly anything pre-2018 won't have them, or very unlikely to have them. EPCs also recognise lower operating temperatures, but they are also not mandatory for under building regs for replacement boilers. Therefore, no one strives for a lower flow temperature for gas boiler systems, and part of that is embedded in a lack of understanding amongst installers that condensing gas boilers are low temperature systems. They are much more efficient at a lower operating temperature. And had we known that for the last 17 years, households could have been routinely upsizing their radiators. We have much more efficient systems right now. We'd be used to longer and lower patterns of heat, and we're still sucked into hot and high. And we'd have a housing stock possibly ready for heat pumps right now. But that opportunity has been missed. However, you will have seen that there's been a big push around flow temperatures, lowering flow temperatures to 60 on gas boilers, depending on levels of insulation, as this improves efficiency. So it's interesting to understand, just how that works. So condensing boilers were a great leap forward in efficiency. Non-condensing boilers lost 20 to 40% of the energy they used out through the flue, whereas condensing boilers can capture that energy before it leaves the boiler and recycle it back into the heating system. But they have to do this at a lower operating temperature, because we need the steam to turn back into liquid inside the boiler so it can capture it and recycle it. The flow temperatures ideally need to sit around 60 degrees or lower if you have good insulation, in order to achieve a decent level of condensing, the boiler going into condensing mode. And the lower the flow temperature, the more efficient it will be. So I was going to just go through a few basics around flow temperatures and boilers, because it's worth revisiting. So very basically, a combi boiler produces hot water instantly. System and heat only boilers work with a cylinder. You can tell if you've got a condensing boiler, it has a white plastic pipe underneath it. Advice around flow temperatures has mostly been careful to emphasise that it's a safe DIY hack for combi boilers. For households with a hot water cylinder, the boiler nearly is always set up to run a single temperature for heating and hot water. So if you turn down the flow temperature for heating, you also affect the hot water cylinder, and that could affect Legionella. The HSE want to see temperatures kept at 60 degrees C, which is when Legionella is killed off in minutes. It's probably overkill, but installers are certainly very wary of deviating from that advice. So boilers tend to be set to 70, they might be left at 80 degrees C, but at least 70 to keep the cylinder temperature at 60. But this is too hot for the boiler to recycle its waste heat, and it's probably not much more efficient than the outgoing non-condensing boiler. It is possible to run a boiler with a cylinder safely and efficiently, but the boiler has to be capable of running 2 temperatures, one for heating and one for hot water. And if the boiler is capable of it, there might be some valve changes downstream of it, but you can successfully then separate the flow temperatures and compensate the flow temperature. So back to the weather compensation, what we want to be able to do is have a variable flow temperature for heating without affecting the hot water. So it usually takes some bespoke changes to the boiler, and what those changes are depend on the boiler. This is quite a good graph. It backs up what Nathan was saying. If you look at the top graph there, that is an on-off control. So the red dotted line is the set point, so 21 degrees room temperature, and that's the boiler. The wavy line is the temperature out from the boiler or out into the room from the radiators, and it's dancing around the set point because it's running at a single hot temperature. It can't maintain 21 degrees. It's always overshooting the stat. And there's some other factors in there, such as the delay in the signal getting back to the boiler, that it's reached its temperature. There's still heat pumping into the system at that point. So we get this cycling up and down. The bottom graph is a weather or low compensation control, where the boiler can intelligently adjust its flow temperature down in order to meet that set point. It's not dancing about that red line. So it's stopping overshooting, it's stopping cycling, and it's also reducing the flow temperature every opportunity and keeping the boiler in condensing mode for longer. Most combis will run with compensation controls quite simply. It's just rewiring into the right terminals with the right control. Again, with boilers, a bit more complicated. You've got to separate out the flow temperatures, and not all boilers are capable of it, and not even all boilers currently on the market are capable of it. So yeah, we have to tread a bit carefully even with new boiler installations. But there is a consultation, a government consultation out now where that looks to be addressed. They're asking the right questions about it. So we're really positive that this could get rectified in the future. Oh, this is Rob Berridge, our colleague. He talks about boilers in terms of traffic. So good boiler going along the motorway, bad boiler, stop-start of town centre traffic. Yeah, so it's just a decent little visual aid. So I think probably my last slide, and I think we'll go back to having a chat. So weather or low compensation controls aside, as we're moving towards low temperature systems, we need to reduce flow temperatures as much as possible. And 2 things need to happen. The house needs to get bigger, it has to get better at retaining heat. So cavity wall insulation, solid wall insulation, whatever that needs to be. And where you can insulate no further, there are practical aspects to doing that that can be barriers. Radiators need to increase. And as a rough guide, to achieve a 55-degree flow temperature, radiators need to be twice as big. To achieve a 45-degree flow temperature, depending on the insulation levels, about 3.5 times as big. So the insulation is really helping to mitigate the size of the radiators and what can be practically achieved. I think my view on this, as this moves on, and in the absence of an energy efficiency strategy from the government, whereby we're not going to see houses massively retrofitted in a short space of time with their financial assistance, is that we will move towards a situation where 55-degree flow temperatures will have to be enough. They will have to be good enough. And what we need to see then is electricity prices coming down. So whilst the heat pump won't be running as efficiently at 55 as it could at 45, electricity prices come down so that it's still an affordable system. I think I'll probably leave it there for slides.
Thank you, Jo.
Yeah,
Before we move on, there was a question from Richard, just going back to your point about EPCs and sort of how changing to a heat pump might not necessarily reflect better EPC. Richard saying that also at the moment they're not reflecting the current unit costs, the current electric unit costs. And do you know if there's going to be a date for when this is going to be adjusted?
I don't, and do you know what? I've asked someone that I think might know some better answers, some questions around that, because I'm just revisiting it again now. I mean, I think what you can say is that the relative price between gas and electric, it used to be 2.5p for gas, 12p for electric.
Yeah.
Electric seemed expensive at that time, and now it's, well, under the caps it's 10p for gas and 34p for electric. So I mean, it is a bit more favourable for a heat pump with a decent efficiency to come in under an equivalent gas boiler, but it's only a bit more favourable. So I think even if they adjusted it now, it would probably, the ratio is still quite similar. I don't think it would have a massive impact at the moment.
And with the, I mean, not that this is about EPCs, but is there a ready rec now? I mean, obviously there's guidance on the EP itself in terms of what you could do to improve the rating, but is there an actual step-by-step, this is what you can,
well, I mean, I didn't carry on with that bit of the presentation, but if I share again, because I've done this for some other presentations, if I just do it very quickly.
The only reason I asked for the purpose of this presentation is, or this conversation, is just because, you know, you noted there that, you know, vast majority of houses that people live in, they already exist, and it's a big retrofitting job to be done. So yeah. You're talking about making your existing heating system become more efficient before, you know, and then move towards,
absolutely,
we're going to be heat pump ready. You know, it's everything else that we can do in the meantime.
It is, yeah. So it's reallocating that budget. So within this presentation, I've got an example of, you know, we've got a 14-year-old broken down boiler, a Valence. Someone might say you need to replace it. It's at the end of its life. Actually, it's got 8 years left of service and excellent parts availability. Yeah. So a repair is £300, a replacement is £3,500. With a small investment, a much smaller investment, you can make it much more efficient. You fit weather compensation controls, and then you get a saving per year, and then your money can be reallocated onto bigger radiators or insulation measures, or getting ready, you know, fitting a heat pump even.
Yeah.
So within the EPC system, yes, there's points there for doing that. And once you've done that, once you've got your 2,500 that you haven't had to spend on a new boiler, that you can then allocate to your radiators, depending on what you need. Cavity wall insulation is a £1,000 investment, and it can add 9 to 11 points onto your, and that's because it knocks a third off of your heating demand. You know, it has a massive impact. Solar PV, £600 saving, adds 7 or 11 points. So there is a pathway for you to reallocate that budget, depending on the type of your, if you have a solid wall house, you might be looking at solid wall insulation, and it's going to have the single biggest impact, 13 to 16 points on an EPC. It's going to take you from, you know, a high E to a C in one lump. So I think you're right, working out the pathway, which is what we tend to do with our customers, to how they best spend their budget. What can they make use of now? Is a new boiler for the next 5 years really going to save them enough money to justify it? Should they just keep it, even if it's a non-condensing model, and wait and fit a heat pump? You know, spend that money on the radiators. So yes, there's definitely a pathway.
Yeah. Okay. Cool. Well, we can share this presentation. I can add that to the webinar notes for later. And then also, I mean, we'll probably come on to this, but you know, Nathan, in the past, I mean, because we're now talking about this pathway to becoming, you know, heat pump ready. But I mean, you've said, Nathan, that we weren't always reliant on one piece of technology for our heating requirements. And so yeah, whether it's heat pump, but it's all of these other things that can be adopted as well, or potentially adopted to ensure that, you know, we're providing, you know, low carbon heating, as it were. Oh,
sorry, Simon, was that? I lost you a bit there.
oh, right. Sorry. Did I break up there? Because I'll stop asking questions if I'm breaking up.
No, I've got you now.
All right, fine. Sorry about that. No, I was just saying, you know, there's a pathway here to become heat pump ready. But, you know, you said previously that, you know, in the past, we haven't always just relied on one piece of technology to, you know, provide our heating requirements.
Yeah, we used to have sort of single point of use heating, didn't we, before we had central heating. Obviously, a heat pump system is a central heating system. If you want to know if your heat pump ready, so the first, I mean, we often hear this thing, fabric first. You know, obviously fabric's very important. If you're cold, you put a coat on, don't you? But the thing I always taught by Grandad is you assess and measure first. So every home is completely different. So you can have two completely the same homes built the same time, but over a period of time, one home might have replaced some rads, or they might have had extensions. So what you need to do is measure what your home needs. So to do that, you need to understand that speed of heat leaving the home. And the best way to do that, we have to do if you put an MCS accredited heat pump installed in for the grant, you have to provide a calculation, a U-value calculation. Now, there's been lots of studies, Leeds Beckett sort of led the way on this 10, 15 years ago. There's been lots of studies that U-value calculations can actually be quite inaccurate because no one knows how well that insulation has been put in the wall. When you do a U-value calculation, you assume that every square metre, because you're basically getting the U-value of a square metre of material, and then you multiply that by the wall's area. But of course, we don't know how well that wall is being constructed. It's usually the labourer on the building site that put the insulation in. They're the lowest paid person on the building site. It's not always been done well. So you can actually measure the speed of heat. So that's what they're starting to look at now, and that's what I do. So I put temperature sensors in someone's home. I put about 6 in someone's home, leave them there for a month. Their data log is, so they're logging the temperature. I also take meter readings before and after the test. I'll take the floor area, which you can get off the EPC. I'll take the window area and the orientation of windows, and then an algorithm will look at the weather data for that month that I've tested. It will look at the solar, the radiation on windows, and then it will give you what's called an HTC. And an HTC is short for heating transfer coefficient. That gives you the speed of heat leaving that home at any temperature outside. So an HTC, let's say you had an HTC of 300, what that means is 300 watts per Kelvin. So every time you get a difference in temperature of 1 Kelvin, you're getting a difference of 300 watts. And all you do with that is times. So let's say it was -3 outside and you wanted 21 degrees inside. That's a difference of 24 degrees. You times that 300 by 24. That tells me what I would need if it was -3 outside. So 24 times 300 is around 8,000. So I would need 8,000 joules per second of heat going into that home. Now that might sound a bit convoluted. 8,000 joules per second is actually 8,000 watts, 8 kilowatts. That's what watts is. 1 watt is 1 joule per second. I now know what that home needs. I then would look at what my radiators can do. Now, so when I started plumbing in the 80s, late 80s or 87, you'd buy things like boiler packs, and it would come with your rads already. And most rads at that time are now going to be double panel, double convector. So there's going to be instances where people have radiators that actually can be able to provide the amount of power to have a low temp heating system, which is what you want. Someone put a question in there. The lower you can get that flow temp for a heat source pump, a heat pump system, the better, because your compressor won't have to work so hard. It only has to sort of get the water up to a certain temperature, and that temperature is then able to put the power into the room. So the two things you do is measure what your home needs, measure what your radiators can put into that home. And then you've got a real good understanding of what you can do. You might need to replace a couple of rads. Sometimes people don't have to replace rads. Sometimes people have to replace quite a few. So it's always horses for courses. You need to understand what each individual property is doing. It's worth pointing out that the average home in the UK, and there's all different sorts of homes, as we know, but the average home in the UK needs 8 kilowatts of power when it's -3 outside. So that's actually not a lot. If you look at the condensing combination boilers, the average size is around 24, 30. They're very powerful because you have to heat water instantaneously to come out your hot tap. But they're too powerful for our heating requirements. So once again, if you were controlling them with just an on-off thermostat, it makes no sense whatsoever, because a lot of homes only need, a new build is only going to need about 3 kilowatts when it's -3 outside. And we've got these massive boilers going in. that Joe knows, that some of them can only range rate down to 7 kilowatts. So they're never hardly condensing.
Yeah.
So yes, look at what your home needs. The speed, the heat that your home needs is the first thing you need to do. Measure it.
Yeah. Cool.
There's a lot of certainly if you've got a combi boiler, you know, the advice around flow temperatures, you can start to test your system. You know that if you fit a weather compensation control and you think as there's ways around it, but as Nate says, if you can work out your heat loss, watts per square meter loss, which is just the kilowatts, 8 kilowatts divided by your floor area, you get to that figure, it'll give you a sort of between 30 and maybe 120. So at 30, it's very well insulated. At 120, it's poorly insulated. So that within there somewhere, there's probably a clever calculation for what your flow temperature needs to be, although obviously it is also based on the size of your radiators. But if you think, well, I'm reasonably well insulated, I think I can run a top temperature at -2 at 60 degrees. When you fit a weather compensation control, you set the curve within the boiler to say my top temperature is 60 at -2. And then it will work out through the year what your flow temperature is. And this is obviously some of the efficiencies available in condensing gas boilers. But also you might be able to set it at 50 and see how you go, you know, and actually how close are you to staying warm through the colder months with a top temperature of 50 or a top temperature of 55. And if you do stay reasonably warm, perhaps your boiler has to run for longer and it follows more of an underfloor heating pattern of continuous heat rather than on-off periods of short and hot operation. Then that is the best, almost one of the best ways of finding out as a quick hack, you know, whether it would work. There's obviously other factors in that, and you probably need to put some gauges on the flow pipes just to understand what properly what the temperatures are. But that's one way of doing it. And obviously, if you can separate the flow temperatures for heating and hot water, if you've got a cylinder, then you can also test that way as well.
Okay. Cool. Thank you.
There's an interesting question from Charles, isn't there? Why do presenters think there is an assumption that heat pumps won't work in an existing building stock? It's a good question, Charles, because what lots of people don't realise that millions of people every day are heated by heat pump technology. So all a heat pump is, and they're everywhere, is something that moves heat from an evaporator to a condenser by vapor compression. Compressor compresses a refrigerant, moves heat from an evaporator to a condenser. They're everywhere. So that costs a coffee machine that in the garage, that's got a heat pump keeping milk below 5 degrees. It's a slush puppy machine. All your vending machines are using heat pump technology, and millions of people go to work every day in office spaces that are heated with heat pump technology. We look up in the ceiling and people think it's air conditioning, and they realise that it's removing heat in the summer to keep them cool. They probably don't realise it's also keeping them warm in the winter. Now, they're air-to-air systems. These are air-to-air systems, and we've tended to, I know DEC, when they were talking about heat pump systems, they thought all sort of heat pump systems in the home had to be air-to-water, water being in the RADs, but they can be air-to-air systems. So any property can be heated with a heat pump. You just need the right size heat pump, the right size emitters to emit the power into the home, and then the pipe work, if it is a water system, pipe work has to be sized correctly to get the energy from one to the other. So there's no problem with, you can heat at home with body heat. So one of the things I always say is you can heat at home with 37 degrees, that's body heat. So if we take my home that needs 8,000 joules per second, you have a party with 80 people jumping about, all emit 100 watts. And so that'll heat the home, and we actually have to take that into account. So when we do cooling, my family does a lot of work, and we've got Ryan here from Dakin, so we put a Dakin system into Classic FM in 1991. We do a lot of radio stations, BBC studios. They've all got heat pump systems. They've had them for like 4 decades. And body heating can be a problem. So 1984, we had Band-Aid. Lots of musicians turned up. Too much body heat, so we had to tweak the heat pump system to remove more of the body heat. So heat pumps have been around us a long time. Obviously, when we talk about domestic, people think of air to water heat pumps, but things like flats and stuff are going to be suitable for air to air, and very cheap technology actually.
Cool. Just, I thought I saw a question before we move on. I thought I saw a question from Anne Williamson regarding radiators, but I can't seem to find it. So I don't know whether if you want to repost that, Anne, that would be quite handy. And there is talk there about hydrogen as well, but that might be a whole separate conversation. Shall we move on then, Guy? I mean, what are some of the other things to look forward to and some of the challenges? And obviously we have spoken about, I saw today that, Germany is forging ahead. They've sort of 55% uplift a year in terms of the amount of heat pumps that are being sold. So, we are, and you've mentioned it just earlier about the Netherlands and Portugal seems to be sort of making, we're not adopting the same level of technology at the same pace as some of the countries in Europe. And I don't know whether the German figure gives us hope, because equally you read a lot about how we're going to get to these figures that the UK needs because of the lack of talent. And
but I thought we haven't committed to it really, even though we talk about figures and how many we want to fit, the policy continually falls short on actually delivering it. And when you look into what a lot of the countries did in Europe in order to jumpstart heat pump adoption, there was an awful lot of community facing communication. So they are out in local town halls and community centres, and really finding ways to reach the population, to talk to them face to face, or giving them access to other people that have had a heat pump, championing those experiences. And I think that is sorely lacking, and we don't have any big advocacy drive to take up heat pumps, that it is our future and committing to it. And part of it is around, I feel, the sort of the mixed messaging around hydrogen. So I know we're not really going to touch on it because nobody thinks that we're all going to be running on hydrogen at all. And even if hydrogen is a viable technology, it won't be for about 20 years. But the government refused to take a position on it. They're not going to give us a timeline. Nobody gives us a timeline. And so we've got the hydrogen PR lobby, putting hello hydrogen up and just confusing people about what that is. So I think we just need very clear lines of communication on what the future looks like for all of us, and that also needs to extend to, if you live in a block of flats, you're probably going to run on a district heating system, or some sort of communal system. So I think we just haven't committed to it. And also there's obviously a lot of mechanism work as well around pricing, affordability, and I think more people would pick it up if they thought the running costs were going to be lower. So, even a dedicated heat pump tariff, maybe if that was slightly subsidised for 2 years, something to really encourage people to make the upfront commitment and feel secure that the running costs are not going to run away from them.
Yeah, I mean, again, the earlier one you mentioned about how the price of electricity needs to come down, but that's not something we can rely on or control. And if that is required, then it's going to make people nervous. Well,
it does make people nervous, and I think the anxiety is also around the heat pump not running efficiently, and that is also not within their control. So even if heat pump prices were, even if energy prices were, perhaps 20p a kilowatt hour, who's to say that the efficiency of the heat pump isn't going to be more than 1 unit in and 2 units out, despite what it says on the paperwork, because the skill set is just not there yet. So I think there's a lot of perhaps technological developments that need to pick up the shortfall in installer skill. We need to take a lot of that away from them somehow, that installers are not wholly responsible for the performance of the heat pump, that somehow technology is going to fill those gaps and plug and play a bit more, perhaps, and in order to guarantee it. Or we start to look at, not having individual homeowners having to discern for themselves which is a good heat pump, which is a good installer. There's so much on them. Actually, if we just had asset companies or energy providers that were putting heat pumps in, they own heat as a service, basically, they own them. We just pay a cost for renting them almost, and paying for our energy, that the responsibility for the installation, for the efficiency, for the maintenance sits with the energy provider or some other provider.
I presume that's where Octopus are going.
I don't know. Nathan might know more. I don't feel at the moment they're offering it as a service, are they? They're
not doing it as heat as a service.
No, they're just doing a decent job on trying to streamline heat pump installations for certain homes, certain house sizes.
I'm kind of pushing, because if you're going to have energy suppliers be installers as well, Octopus and BG, I think Ofgem should mandate that some of their installs are actually monitored.
I think they should all be monitored. Yeah, I think,
because if you look at what BG have done with boilers, they've put them in a very, they haven't considered best practice. They've just been controlling them on and off, so people are actually paying more for gas than they need. And it's the same with a heat pump. I think 3G and Octopus are going to be putting heat pumps in that are going to be designed to slightly higher temperatures than what sort of the good engineers I know will be putting them in. So you're going to be paying more for your energy. Because the secret sauce to a heat pump is, they call it narrowing the delta T between the sink and the source. What does that mean? Well, the source, air source heat pump, you're getting your energy from your air. Sink is what we call the temperature running around your rads, basically. And if you can narrow the delta T, the difference in temperature between those two, so if you've got like 0 degrees outside and a rad with 35 degrees inside, and it's maintaining heat in your home, that's going to be more efficient than if it was 0 degrees outside and you had to have rads with 45 degrees in your radiators maintaining that comfort in your home. So you narrow them two temperatures. That's the secret sauce to a heat pump system, air to water heat pump system. Obviously, air to air is a little bit.
Okay. I mean, I suppose we were just talking earlier on, Redrow announcing today they're going to be installing heat pumps as standard from from next month, I think it is, into detached houses. Then that, I mean, that's definitely a good situation where house builders are now starting to see the light and take action and do that. And one would hope they would have. That goes back to your measurement point as well. Then, so new builds is slightly different and easier than retrofitting, because they can do that modelling and that measurement before, because they know the type of house they're building, and therefore they can hopefully employ the people to do the measurement, to then put the right size heat pump in etc. Those new houses will become more efficient, and people are confident with what they're getting from having a new heat pump installation. Although when they move into the house, they don't know there's no installation, it's already been done. So
developers had their fingers burnt. I mean, some developers were doing this 15 years ago, and of course what was happening was the people putting them systems in for the developers weren't commissioning them properly, hadn't designed them properly, and of course the homeowners were then getting very high bills. So a lot of the developers thought, we won't do that again.
No. I mean, through the Heating Hub and your podcast, and people are becoming more will have the opportunity to become more knowledgeable, because it is complicated when you talk about measuring the flow of heat leaving. I mean, it is complicated, and Graham Hendry always talks about the fact that this needs to be, just keep it simple. Like you know, whilst we've said about the marketing exercise behind gas boilers, you know, it's just like selling white goods, but in some ways heat pumps don't need to talk too much about the technology, because it can get quite complicated. And it's like, this is what the heat pump heating system can do, and that's it. And so it is there's an opportunity to ensure that from an education perspective, it's, you know, householders are confident that it does what it says on the tin. But
I think that's really important. I think that where the problems in gas heating have been is that it hasn't done what it's done on what it said on the tin, but we've had no indicators to show us that. So we've had underperforming gas boilers, but because gas is cheap and the boilers are quite forgiving, no one's noticed. But that means that we haven't got the kind of accountability, checks and balances in our heating industry, or the training that was needed to maybe bring the A-rated performance about. So we're just sort of sorely lacking. And I think for consumers, what they want is to be presented with a solution that works, and feel confident in the background stuff that is taken care of, that regs are high, that installation standards are high, that the commissioning process is meaningful, when they're told they're going to get 3.5 as a SCOP, that's what they get, you know, and it's monitored. That needs to be much more robust. And then I think people would make that transaction very easily. You know, you think, I feel confident that's always going to happen. At the moment, that isn't there in the background, so that it sort of sits back with the the homeowner to make a better decision, or to be responsible for their own decision, which is inevitably a bad one, because if you're presented with 3 bad quotes, you're going to have a bad, it's just not there at the moment.
We've only got 5 minutes left. Was there anything else you two would like to cover, or that you plan to cover?
I'll look back at my list.
Because otherwise, I mean, something else came up, Nathan, in terms of, and it's, you know, if the UK, if we plan to install 600,000 heat pumps a year, then can the grid take it? And there's, I don't know whether there's misinformation, or again, there's uncertainty, because, you know, some people are saying the grid can't, but they've come out and said that it's all fine, it's all fine.
Well, it's definitely not my area of expertise.
Right. Okay.
I've had people on the podcast that do know about. I mean, it's always worth remembering that people think these heat pumps use lots and lots of energy, and of course, if they've got a COP of 3, you know, you're only sort of talking about an input of maybe 2 kilowatts into the. I mean, when people used to switch, I mean, I know we all have lots of channels now on telly, but you know, back in the day when Coronation Street was on, or the World Cup, you know, people would go and switch their, a few million people would switch their kettles on 3 kilowatts each, and you'd have to, you know, the grid would have to bring on extra power